So this is a lecture in continuation with the problems on the reducibility and irreducibility of polynomial. So this is problem number 11. It was asked in NET June 2015, part C. Determine which of the following polynomial are irreducible over the indicated rings. So we are interested in the irreducible polynomial. First of all, irreducible, and here R, Q, Z and Z quotient 2Z. So let me first of all clear it is what it is Z2. Okay, so let us go one by one. So if we look at option A, then fx is what x raised to 5 minus 3x raised to 4 plus 2x cube minus 5x plus 8, and degree of fx is equal to 5, which is greater than or equal to 3. So belongs to, it is asked over R. So implies fx is reducible, because we know that any polynomial of degree greater than or equal to 3 over R is always reducible. So option A is wrong, because we are interested in irreducible. Now for option B. So here therefore option A is wrong. Now option B, you say fx is equal to x cube plus 2x square plus x plus 1 over qx. Here degree of fx is 3 and q is a field. So fx is reducible over q if and only if fx has a 0 in q. So suppose fx is reducible over q, implies fx has 0 in q, because degree of fx is equal to 3. So let alpha is equal to r by s with GCD of r and s equal to 1 be a 0 of fx in q. So by rational root theorem, what we have, r will divides the constant term and s will divides the coefficient of leading term or leading coefficient. So it gives me r is equal to plus or minus 1 and s is also plus or minus 1. So alpha is equal to r by s is what, plus or minus 1. So by manual calculation, f of 1 is what, 1 plus 2 plus 1 plus 1 5, which is not 0, and f of minus 1 will be minus 1 plus 2 minus 1 plus 1. So it is 1, which is also not 0. So therefore f of x has no 0 in q. So therefore fx is irreducible over q. So therefore option B is correct. So option B is correct. Now third one, option C. In C, so let gx is equal to, it is what, x cube plus 3x square, x cube plus 3x square minus 6x plus 3 over zx. See, this is what, clearly gx is 3 Eisenstein. So therefore gx is irreducible over q. Therefore gx is irreducible over z because gx is monic. So if it is monic, then irreducible over q implies irreducible over z. So therefore option C is correct. So option C is correct. Now option D. For option D. So option D, so you take let hx is equal to x raised to 4 plus x square plus 1. So it is over z2x. X raised to 4 plus x square plus it is over z2x. Now z2 is 0, 1. So h of 0 is what? 1, not equal to 0. H of 1 is what? 1 plus 1 plus 1, it is 1, which is not equal to 0. So this says that hx has no 0 in z2. So it means hx has no linear factor in z2x. So it has no linear factor over z2. So now degree of hx, is equal to 4 and hx has no linear factor. So if hx, so thus if hx is reducible over z2, then hx must be product of two irreducible quadratic polynomials. Now in z2 x square plus x plus 1 is the only irreducible quadratic polynomial. Now to have hx reducible over z2, it must be product of two quadratic polynomial, and this is the only quadratic polynomial which is irreducible over z2. So if hx is irreducible, then it must be product of this polynomial with itself. So let us check whether it is so or not. So now let me check it by direct calculation. So let x square plus x plus 1 into x square plus x plus 1. So it gives x raised to 4 plus x cube plus x square plus x cube plus x square plus x square plus x plus 1. So x raised to 4. Now x cube 2 times. I have x cube is 2 times, so it is 0. X square 3 times, so x square plus x square 0, and we left with only 1 x square, and xx is 2x, it is 0 in z2. So we left with x raised to 4 plus x square plus 1, and it is not hx. Sorry, it is let me see what is hx. X raised to 4 plus x square plus 1. So yes, it is hx. It is equal to hx. So therefore hx is reducible over z2. So therefore, but we are interested in irreducible, so option D is incorrect, wrong, because we are interested in irreducible, so option D is wrong. Now problem number 12. So which of the following polynomials are irreducible in the ring Zx? So again here we are interested in irreducible. A polynomial in variable with integer coefficient. So that is just definition of Zx. So here we want to check which of the following polynomial is irreducible over Zx. So if you observe, then all the polynomials are monic polynomial, first thing. Second thing, degree of polynomials in option A is 2, in option B it is 4, option C 4 degree polynomial, and option D 3 degree polynomial. So now let us go for option A. Fx is equal to x square minus 5. So it is over Zx. So clearly Fx is phi Eisenstein. So therefore Fx is irreducible over Q. So therefore Fx is irreducible over Z, because Fx is monic. So therefore, and we are interested in irreducible polynomial, so therefore option A is correct. So option A is correct. Now for option B, say gx is equal to 1 plus x plus 1 plus x plus 1 square plus x plus 1 cube plus x plus 1 raised to 4. So it is over Zx. So now you consider g of x minus 1, then it is what, 1. So you just replace x by x minus 1. See what you are doing here, you just replace x by x minus 1. So it gives me x plus 1 is equal to what? It is x. So it is x plus 1 square is x square plus x cube plus x raised to 4. But this is what? It is phi x. So it is also in Zx. So phi x is what, fifth cyclotomic polynomial, so it is irreducible over, it is a fifth polynomial. So therefore g of x minus 1 is irreducible over q. So therefore g of x is irreducible over q. Why? Because minus 1 belongs to q is unit, and we know that result, let me state the result here, f of ax is reducible, let me write in the form of f of x plus a is irreducible, implies f of x is irreducible where a belongs to f and it is non-zero. So we know this result. So therefore gx is irreducible over q. So therefore gx is irreducible over z because gx is monic polynomial. And you observe gx is what? It is x plus 1 raised to 4, and the degree of gx is 4, and the coefficient of x raised to 4 will be 1 on the binomial expansion of x plus 1 raised to 4, and there is no term which gives x raised to 4 among this x plus 1 cube and so on. So gx is monic, so gx is irreducible over z, and we are interested in irreducible polynomial. So option B is also correct. Now for C, for option, so here therefore option B is correct. So option C, let me say it is hx. Hx is what? 1 plus x square plus x cube plus x raised to 4. So it is what? It is phi of phi x. So it is what? Fifth cyclotomic polynomial. So therefore hx is irreducible over q. So therefore hx is irreducible over z because h is monic. So therefore option C is also correct. And option D, for D you let tx is 1 plus x square plus x cube, but it is what? 1 plus x square is common, then it is 1 plus x, and it means what? It is 1 plus x into 1 plus x square. So it is what? Reducible over z. So therefore option D is wrong. So option D is wrong. So correct options are A, B and C. Now problem number 13. It was asked in June 2014, C part. Fx is given, it is a 4-degree polynomial, and P be a prime, and let Fpx denote the corresponding polynomial with coefficients in z quotient Pz. So let me consider, this is exactly what it is, Zp. Then f2x is irreducible over z quotient 2z means it is z2. Fx is irreducible over q, f3x is irreducible over z quotient 3z means z3, and fx is irreducible over z. So here two options are about over Z2, Z3, that is ZP, and two options B and D are over respectively Q and Z. So let's consider first one. So for option A, you consider fx is equal to x raised to 4 plus 3x cube minus 9x square plus 7x plus 27. So it is over zx. Now f2x, so it will be in z2x. So you reduce the coefficient of fx by modulo 2. So it is x raised to 4 plus x cube, 3 is 1. Now minus 9 is plus 1. So it is x square plus 7 is plus 1 and 27 is plus 1. So it is over z. So by inspection f2 0. Now z2 is what? It contains two elements 0 and 1. Now f2 0 is 1, which is not equal to 0, and f2 1 will be 1 plus 1 plus 1 plus 1 plus 1. Again it is 5, which is equal to 1, which is not equal to 0. So f2 has no 0 in f2x has no 0 in z2. f2x has no 0 in z2. So therefore f2x has no linear factor in z2x. So suppose f2x is reducible over z2, then it must be product of two irreducible quadratic polynomials in z2x. And we know that x square plus x plus 1 is the only quadratic factor. Irreducible factor, quadratic irreducible factor in Z2. So by manual calculation, therefore x square plus x plus 1 into x square plus x plus 1, we have seen in some previous example. Yes, it is there. So that is what? It is x raised to 4 plus x square plus 1. It will be x raised to 4 plus x plus 1, and it is not f2x. So therefore f2x is irreducible over z2. So therefore option A is correct. So therefore option A is correct. Now over Q. For option B, let fx is equal to x raised to 4 plus 3x cube and so on plus 27 belongs to zx. It is given. Now I want to check its reducibility over Q. So now you consider f2x belongs to z2x. So f2x is what? F2x is a polynomial corresponding to fx whose coefficients are reduced by modulo 2. So implies we have discussed in part A f2x is irreducible over z2. So implies by modulo p test fx is irreducible over q. So therefore option B is correct. So here option B will be correct. So now let us go for part C. In C, f3x is irreducible over z3. So here fx is what? Fx is x raised to 4 plus 3x cube minus 9x square plus 7x plus 27, and f3x will be what? This is in zx. So f3 will be x raised to 4. Now 3 is 0, 9 is 0, 7 is in z3, 7 is x and 27 is 0. So it is x raised to 4 plus x, but it is what? X into x cube plus 1. So this is what in z3x. So this is what? f3x is reducible over z3, and in option C they say it is irreducible. So therefore option C is wrong. In option C, f3x is irreducible over z3, but we get it is reducible. So option C is wrong. Now fx is irreducible over z. In fourth option says that fx is irreducible over z. So for option D. So say option D. Here fx is what? Fx is equal to fx is equal to this belongs to zx. Now if you consider f bar x, and it is equal to f bar x belongs to z2x, then f bar x in our previous notation it is f2x belongs to z2x, and by option we have discussed in part A, f2x, that is f bar x is irreducible over z2. So therefore fx is irreducible over q. So therefore fx is irreducible over z, because fx is monic. So therefore option D is correct. Option D is correct. So now problem number 14. Let fx is equal to this x cube plus 2x square plus x minus 1. Determine in which of the following case f is irreducible over the field K. So we are interested in irreducible over the field K. In option A, field is Q, B R, in C F2. F2 means here F2 is what? Z2, and F3 means it is filled with 3 elements, so it is Z3. So if you see option B, then we know that any polynomial of degree greater than or equal to 3 is always reducible over R, and we are interested in irreducible, so over R it is reducible, so option B is not correct. So let me quickly any polynomial of degree greater than or equal to 3 is always reducible over R, so therefore option B is wrong. Now let us go for option C and D. So now here I have what? fx is equal to x cube plus 2x square plus x minus 1. So it is over z2x, but z2x, if I consider it for z2, then it is x cube plus x minus 1, because 2 equal to 0. Now z2 contains only 2 elements, 0 and 1. So by inspection, f of 0 is minus 1 is plus 1, it is not 0, and f of 1 is 1 plus 1 minus 1, it is again 1, which is not equal to 0. So therefore fx has no 0 in z2, and degree of fx is equal to 3. So therefore fx is irreducible, it is not reducible. Degree is 3 and it has no 0, so it is not reducible, that is it is irreducible over z2, and we are interested in irreducible, so option C is correct. It will be irreducible over z2. So therefore option C is correct. Now option, now you consider it is over q. Here fx is equal to x cube plus 2x square plus x minus 1 belongs to zx. Here I am talking about for option A. So now you consider f bar x belongs to z2x. So f bar x will be what? It is x cube plus x minus 1. So minus 1 is plus 1. So this will be in z2x. So again f bar 0 is 1, which is not 0, and f bar 1 is equal to also 1, which is not equal to 0. So therefore f bar x is irreducible over z2, and degree of f bar x is same as degree of fx. So implies fx is irreducible over q. So therefore option A is correct. So option A is correct. Now option D. So for option D, fx is equal to x cube plus 2x square plus x minus 1 belongs to z3x. So degree of fx is 3, and to check whether it is reducible or irreducible over z3, it is enough to check whether it has a 0 in z3 or not. So you consider f of 1. So z3 contains what? 0, 1 and 2. So f of 1 will be 1 plus 2 plus 1 minus 1. So it will be 3, and it is 0. So therefore fx has a 0 in z3, and degree of fx is equal to 3. So therefore fx is reducible over z3, and it gives me option D is wrong. So option D is wrong. So now problem number 15. So which of the following, in problem number 15, which of the following polynomials are irreducible over, which of the following problems are polynomials are irreducible over given rings? So again problem is about irreducibility, which is irreducible. Option A, B, C, D over Q, then in B over Z quotient 7Z means Z quotient 7Z is equal to Z7, and in C and D over ring of integer Z. So let us start with option A. So here fx is what? X raised to 5 plus 3x to 4 plus 9x plus 15 is over zx, but it is what? It is a 3 Eisenstein. So therefore fx is irreducible over q. So therefore option A is correct. Therefore option A is correct. Now for option B, fx is equal to x raised to 5 plus 3x raised to 4 plus 9x plus 15 belongs to z7x, but over z7 it is x raised to 5. Sorry, the polynomial is different one. Polynomial is x cube plus 2x square plus x plus 1 over z7. So degree of polynomial is 3 and z7 is a field. So to check the reducibility, it is enough to check whether fx has 0 or not. So f of 0 will be 1, not equal to 0. F of 1 will be 1 plus 2 plus 1 plus 1. It will be 5, not equal to 0. G of 2 will be 8 plus 8 plus 2 plus 1, that is 19, but 19 means it is congruent to 5 in Z7, so it is not equal to 0. G of 3 will be 27 plus 18 plus 3 plus 1, it is 49 and it is 0 in Z7. So therefore Gx has a 0 in Z7 and degree of Gx is equal to 3. So therefore Gx is reducible over Z7. So therefore option B is wrong, because we are interested in irreducible over Z7. So B is wrong. Now option C, it is a cubic polynomial, x cube plus x square plus x plus 1 over zx. So now for option C, and option C, so let hx is equal to x cube plus x square plus x plus 1. So if we take x square common, then it is x plus 1 plus x plus 1. So it is x square plus 1 into x plus 1. So this is what? It is over zx. So therefore hx is reducible over z. So therefore option C is incorrect, because we are interested in irreducible. So C is wrong. Now for option D, let Tx is equal to x raised to 4 plus x cube plus x square plus x plus 1. But this is what? 5 x, fifth cyclotomic polynomial. So therefore Tx is irreducible over Q. So therefore Tx is irreducible over Z, because Tx is monic. So therefore option D is correct. So in problem number 15 we have A and D are correct, B and C are wrong. Now problem number 16. Problem number 16. Consider the polynomial, fourth degree polynomial, x raised to 4 minus x cube plus 14x square plus 5x plus 16. Also for a prime number p, let fp denote the field with p elements, that is fp means what, it will be zp. Which of the following are always true? Considering f as a polynomial with coefficients in Z3, it has no roots in Z uh, um, in F3. So F3 means Z3. Consider f as a polynomial with coefficients in the F3, that is Z3. It is a product of two irreducible factors of degree 2 over Z. F3 means Z3. Considering f as a polynomial with coefficients in Z7, that is F7, that is Z7, it has an irreducible factor of degree 3 over Z7, and f is a product of two polynomials of degree 2 over Z. Okay, so here fx is a polynomial of degree 4 and they are asking about the roots of the polynomial in Z3, whether it can be written as a product of two irreducible polynomial of degree 2 over Z3 or not, and similarly for Z7, irreducible factor of odd degree 3 or not, and f is a product of a polynomial of degree 2 over Z or not. So here fx is what, x raised to 4 minus x cube plus 12 plus 14 x square plus 5x plus 16. So for option A, you consider f is a polynomial with coefficient in f3, that is z3. So let me consider it is over z3x. Then our fx will be what? In z3, x raised to 4 minus 1 is plus 2. So it is plus 2 x square x cube plus 2x square plus 2x plus 1. So this is in z3x. You reduce the coefficients by modulo 3. So we have this. So now we want to check it has a root in z3 or not. Now z3 is what? 0, 1 and 2 only. So f of 0 will be 1, not equal to 0. F of 1 will be 1 plus 2 plus 2 plus 2 plus 1, and it is 8. But 8 in z3 is 2, which is not equal to 0. And f2 is 16 plus 16 plus 8 plus 4 plus 1, and that is what, 16 plus 16, that is 32 in z3 is 2. 8 plus 4 in z3 is 8 plus 4 12 is 0 and 1 is 1. So again it is 2 plus 0 plus 1, that is 3, and 3 is 0. So fx belongs to z3x has a 0 in z3, that is f3. So therefore option A is correct. So in option A they claim that it has a 0 or there is a root in f3, so that is correct. Now in option B it says that in option B, it says that um, f is a polynomial with coefficient in f3. It is a product of two irreducible factors of degree 2 over f3, that is z3. So see, by part A we can see 2 is a 0. So let me I need some space, so before me add one more page. Okay, so let us go for option B. By part A, fx has a 0 in z3, that is f3, namely alpha is equal to 2. So therefore x minus 2 is a factor of fx. So now if fx is a factor, x minus 2 is a factor of fx, so what we have, so therefore fx is equal to x minus 2 into qx for some qx belongs to z3x. Now suppose in option B they claim that let me once more read option B. Polynomial, consider f is a polynomial with coefficient in f3, and it is a product of two irreducible factors of degree 2 over f3. Now suppose fx is product of two irreducible now suppose fx suppose it is a product of two irreducible polynomials of degree 2, that is fx is equal to 2 degree polynomial into 2 degree polynomial, and it is say gx, and this is say hx. Okay, now suppose fx, let me consider in this way, let fx is a product of two polynomial of degree 2. Forget about irreducible, you consider just product of two polynomial of degree 2. Then fx is 2 degree polynomial into 2 degree polynomial. Okay, now on the other hand I have fx is x minus 2 into qx. So on the other hand this is what, x minus 2 into qx. So it means what, x minus 2 is a factor of gx. See here x minus 2 divides RHS, and RHS is gx into hx. So x minus 2 divides gx, or x minus 2 divides hx. So x minus 2 is a factor of gx or hx. So if x minus 2 is a factor of gx, then gx is a polynomial of degree 2 and x minus 2 is a factor, so gx is reducible. And suppose x minus 2 divides hx and degree of hx is 2, so hx is reducible. So implies what we have, gx is reducible or hx is reducible. So it means what? If we try to write gx as a product of 2-degree polynomial, then one of them it is reducible. So implies fx is not a product of 2 irreducible polynomials of degree 2. So therefore the option 2 is wrong. So option 2 is incorrect. Sorry, in option A we found that fx has a 0 in Z3, and in option A they say has no roots in F3, but that the given statement is wrong. Sorry, so this is what it should be wrong. Now option C. In option C, you consider the given polynomial in Z7. So here fx is equal to x raised to 4 minus x cube plus 14x square plus 5x plus 16. It is over Z7x. So fx will reduce to x raised to 4 minus x cube plus 5x plus 2. And by inspection you look at and in Z7 is 0, 1, 2 up to 6. So f of 1 will be 1 minus 1 plus 5 plus 2. So it is 7 and it is 0. So therefore x is equal to 1 is a 0 of fx in Z7. So x minus 1 is a factor of fx. And in option what we have asked, in option we say that consider f is a polynomial over Z7. It has an irreducible factor of degree 3 over Z7. So we got one factor, it is x minus 1. So the remaining factor will be what? It is of degree 3. So first of all let us find out that irreducible 3 degree factor. So by synthetic division, so we will find that factor x raised to 4 this space will be okay. Let me try. X raised to 4 minus x cube plus 5x plus 2 divided by x minus 1. So x cube, so it is x raised to 4 minus x cube, so minus plus, so it gives me 5x plus 2, both will be cancelled, and plus 5 it gives me 5x minus 5, so it gives me minus plus, so it is 7, and 7 means it is 0. So therefore x raised to 4 this fx is equal to x raised to 4 minus x cube plus 5x plus 2 is x minus 1 into x cube plus 5. So this is 3-degree polynomial, and in option C we have asked it has an irreducible factor of degree 3 over z7. So factor 3-degree factor is x raised to 5, x raised to 3 plus 5. So now you consider gx is what? X raised to 3 plus 5 is a 3-degree factor of fx in z7x. So now we want to check whether it is a reducible or irreducible. So it is a polynomial degree 3, and to check whether it is reducible irreducible, it is enough to check whether it has a 0 in z7 or not. So z7 is 0, 1, 2 up to 6. So g of 0 will be 5, not equal to 0. G of 1 will be 1 plus 5, that is 6, not 0. G of 2 will be 8 plus 5, it is 1 plus 8 means 1, and 5 is 5, so it is 6, again not equal to 0. G of 3 will be 3 cube plus 5, and 3 cube is 27 plus 5, and 27 means it is 6 plus 5, and that is 4, and that is not equal to 0. So see, not that we are working in z7, so at every step I am using modulo 7. So g of 4 will be 4 cube plus 5, and 4 cube means it is 16. 4 cube, it is 64, so it is 16 into 16 plus 5, but 16 means 2 plus 5, so it is 9. 9 means 2, so it is not 0. G of 5 will be 5 cube plus 5, and 5 cube, so it is 5 square into 5 plus 5, and ultimately it will be, so we are working in z7, so it is ultimately 6, and then it will be 4 into 5, 25. 25 in z7, 7 3 is 5, 25 in z7 is 4, yes, 7 3 are 21, so it is 4 into 5 plus 5, so it is 20 plus 5, so it is 25, and 25 means 4, so it is again not equal to 0. And g of 6 will be 6 cube plus 5, and it is 6 cube, so it is 36 into 6 plus 5, and 36 is what? It is 1 into 6 plus 5, so it is 6 plus 5, so again it is 36, so 11, and 11 means 4, it is not equal to 0. So therefore gx has no 0 in Z7. So therefore gx is irreducible over Z7. So therefore fx has an irreducible factor of degree 3 in Z7x. So therefore option C is correct. Now f is a product of two polynomials of degree 2 over z. So from option C, so let us so let me add one more page here. So let me delete this. First of all, I have added wrongly. Delete this page, and now let me add after. Okay, so this is what, yes, I have to add after this page, this one, add page. So this is new page. Okay, now for option D. In option D, it says that f is a product of two polynomials of degree 2 over z. F is a product of two polynomials of degree 2 over z. So from option C, what we have? So let me start with option C. From option C, fx is equal to x minus 1 into x raised to 5 plus 5, sorry, x cube plus 5. It is belongs to Z7x. So you may consider, so see, you may consider in this way. See, you consider fx is equal to, fx is our polynomial, what is the polynomial fx? It is x raised to 4 minus x cube plus 14x square plus 5x plus 16. It is over zx. But you consider f bar over this, then by option C. F bar is this one. Suppose fx is product of two polynomials of degree 2 in zx, then what I have? Fx is equal to gx into hx for some gx hx belongs to zx, and degree of gx is equal to degree of hx is equal to 2. So implies fx bar is equal to gx bar into hx bar belongs to, if you consider z7 in z7x, then this is a polynomial of degree 2 and this is also a polynomial of degree 2, but that is contradiction with this. In z7x we have f bar x is x minus 1 and x cube plus 5, and x cube plus 5 is irreducible. So f bar x is not a polynomial of product of polynomial of degree 2 and polynomial of degree 2 and which are irreducible. So this is a contradiction with star, and let me say this is what star. So let me give once more argument. See, suppose fx is a, you start from here. Suppose fx is product of two polynomial of degree 2 in zx. Product of two, in fact they are saying irreducible polynomials. Sorry, no, only product of 2 degree polynomials. Then fx will be gx into hx, and degree of gx and hx are 2. So now you consider this expression in z7, then we have this thing, and in from option C we know that f bar is a product of 1 degree into 3 degree polynomial, and this 3 degree polynomial over z7 is irreducible. So in z7 f bar x can be written in this way only. So suppose if we assume fx in this way, then we get f bar x as a product of 2 degree polynomial in z7, but we have proved that it is not a product of 2 degree polynomial, because we get only one factor of 1 degree and another factor of 3 degree, and that 3 degree factor is not reducible. If 3 degree factor is reducible, then we get 2 degree factor. So therefore with this expression star we get contradiction here. So I hope you understand this argument. So therefore what we have, therefore option D, therefore we have option D is wrong. So finally option D, where it is option D is wrong. So in problem number 16 only one correct option, that is option C. So now we have some more problem on but we will discuss the next problems in next lectures. Thank you.